Welcome. In this video, we are going to talk about interpreting data from page 6 from this rate law lab. And a reminder, there is a video link here at the top. This is a 12-minute video, but we only need the first few minutes until about the time point 3:30. That's when the relevant data collection ends. Feel free to watch more of it if you are interested, but we only need the first few minutes here. And the goal behind this is we're trying to determine the rate law for this reaction right here. This is known as the iodine clock reaction, and it is a cool reaction that we use in kinetics because we can see this turn from clear to blue. So it's a very clear indicator of when the reaction has reached a certain point. So this is the reaction. Again, I'm trying to find the rate law of it. And just a reminder what that means, what a rate law looks like is its rate equals some constant K times the concentration of the reactants to some exponent. So I'm just going to write a generic version up here. So our goal, so I'm just putting X, Y, Z for now. Our goal in this reaction is to figure out the values of X, Y, Z. So we're trying to figure out the reaction order for these three reactants. And if you look at the lab, the way that we're going to measure this is we're going to measure the amount of time it takes for the reaction to turn blue under various experimental conditions. And this introduction talks a little bit more about the chemistry involved here, but I'm going to skip past that and just focus on the data interpretation. Okay, so there were 4 beakers that he had set up in the video, and the idea is that we want to watch the video and use the actual time points from the video itself and to figure out how long the reaction took. And so my time points might be different from yours depending how we judge this, but they should be in the same ballpark, maybe like within plus or minus 5 seconds, I would think. So for the baseline, I measured that one that the reaction started at 38 seconds and it turned blue at 192 seconds. And here's the experimental setup. There were 5 things that we mixed together in the beaker. One is this sodium thiosulfate. We had water, potassium iodide, chloride, bromate. So remember, when you stick these in solution, they're going to ionize. So your Ki, that's the source of your iodine ions. And then this is your source of your H plus ions, because that's a strong acid. So it's going to split apart and form hydrogen ions. And then this one right here is the source of your bromate ions. Okay. And notice that the total volume here is 50 milliliters. So that's our baseline. And it turns out this reaction mixture took 154 seconds to turn blue. All right. Then we do experiment 2. And in experiment 2, the only difference is we eliminated the water and doubled the concentration of iodine. So we still have a 50 milliliter volume, but now we have double the concentration of iodine. And the amount of hydrogen and bromate and everything else are still constant. So this allows us to, and these reactions were carried out at the same temperature, they were carried out in the same size beaker, so all other variables stayed the same. The only difference is we doubled the concentration of iodine ions here, because we added twice as much iodine. And then we want to see what impact this has on the rate. And so notice here, this looks a little bit different from practice sets we may have seen, because we don't technically have a rate value, like we don't have a reaction rate. We could calculate it, but that would involve several complicated steps. And we kind of have all the information we need here. So what we do know is the time it took for the reaction to turn blue. And just the way this reaction works is the reaction turns blue when all of your sodium thiosulfate gets used up. I feel like I should point this out. It goes into more detail about this up here, but when all your sodium thiosulfate gets used up, that's when it turns blue. And we're adding the same amount of sodium thiosulfate in every experiment. So that's key to know. So this part is the same. The only thing that's going to be different is how long it took for it to turn blue. And if you compare these two values here, what I'm going to do is this. I'm just going to say 154 divided by 65. I can tell it's going faster. 65 seconds is a lot faster than 154 seconds, right? And if I divide these two numbers and divide my bigger number by my smaller number, it looks like it's going about 2.36 times faster. So if I stop and think, okay, what is my data telling me? My data right here, when I compare experiments 1 and 2, it's telling me that when I double the concentration of iodine, my rate goes 2.36 times faster. Okay, and we're going to try and use this information to figure out the reaction order. And remember, our possibilities are, for my reaction order, are that it could either be, we're focusing on iodine here, it could either be 0th order, it could be first order, or it could be second order. Those are my three possibilities I'm trying to distinguish between. So if we think through those scenarios, if we were to double the concentration and it were 0th order, it would have no impact on the rate, because anything to the power of 0 is 1. So it doesn't, so if it's 0th order, no matter what you do to the concentration, the rate won't change. So it's definitely not 0th order, because it definitely got significantly faster, right? So it seems like it's either first or second order. So if it were first order and we doubled the concentration, the rate would be twice as fast. If it were second order and we doubled the concentration, 2 squared is 4, so the rate would be 4 times as fast. And since this is real life data, it's not perfectly pretty, right? We got 2.3. It's not exactly 2, it's not exactly 4, but we can ask ourselves, which is it closer to? And 2.3 is much closer to 2 than it is to 4. So based on this data, I'm going to say that it looks like iodine is first order. Okay, so I had to step away for a moment, but I think where we took a break is we just talked about the idea that it looks like iodine is first order, okay? And that's because when we double the concentration of iodine, the reaction turns blue about twice as fast. It's not exactly twice as fast, but it's about twice as fast. Again, this is real data, so it's not going to be perfect. Okay. So let's look at, and notice that bromate is very similar. So we're going to draw a very similar conclusion for experiment 3 with bromate. So I'll let you kind of do the math here and see how much faster it got. Let's look at one more. Let's look at the 4th experiment where we double the hydrogen ion concentration. And we might notice that this one was dramatically faster. So you might already have kind of a guess as to what the reaction order is for hydrogen, but let's confirm this with data. So if we compare experiment 1 and experiment 4, we want to make sure we compare the right experiments. We want to compare these two because what happens in experiment 1 versus experiment 4 is everything else stays the same except I double the concentration of hydrogen ions and every other reactant stays the same. So that's key. You have to compare data sets where only one variable is changing. So the variable here is the hydrogen ion, and we are doubling the hydrogen ion concentration. And if we compare the rates, I'm just going to take my original time it took to react divided by my new time it took to react. And again, this isn't actual rate data, it's just time to react, but we can kind of get the same sense here of how much faster it's going. So it looks like this is about 4.6 times faster. Okay, so when we double the concentration of hydrogen ions, the reaction went about 4.6 times faster. And again, we want to think about our different possibilities for reaction order. So the reaction order could be 0th order. If it were 0th order, then no matter how we change our concentration, the rate would not change. Okay. First order would mean that if we doubled the concentration, the rate would also double. And then this would be second order. So again, let's try plugging in numbers here. So if I doubled the concentration and it was 0th order, the rate would not change. If I doubled the concentration and it were first order, the rate would be 2 times faster. And whoops, and if we double the concentration and we're second order, the rate would be 4 times faster. And what we got is 4.6 times faster. So what seems to most closely match our data is this right here. So it seems that the hydrogen reactant is second order. So that's how we want to interpret data in this lab. You want to, you're going to double one of the concentrations, either iodine or bromate or hydrogen, and then you're going to see how much faster the reaction went compared to the baseline. So it's important you always compare this time to that original time in experiment 1 to see the impact of doubling the reactant on the reaction rate. And please follow up with any questions, additional questions you might have on this. Thanks for watching.